Hello everyone, this is Finnur Pind from Treble Technologies, here with yet another feature launch webinar. I'm very excited to be with you all here today to showcase some new and very cool functionality in the Treble Acoustic Simulation Suite. This is the outline of today's webinar. I will begin with a very short introduction and overview of our simulation platform, and then showcase various new features that are being launched or have been launched very recently. I will then give the word over to Ólafur, who will show a very interesting presentation about some very interesting work that he has been doing, acoustics related work, and has been using Treble for this purpose. And then in the end we will do a Q&A where we will answer any questions that might come up. So please shoot in your questions along the way during the presentations or afterwards if you like. So let me just dive right into it. First, briefly explaining what Treble is. I'm assuming that most people here today are familiar, but just to put us all on the same page, Treble is a sound simulation platform, a next generation sound simulation platform. And the way the thing is structured is, as is shown here, so we have three kind of main pieces, moving pieces. First of all, we have our sound simulation engine, which sits in the cloud. And then we have kind of two interfaces or two products on the market that interface with this simulation technology. On the one hand, we have the simulation suite, which is what we will be talking about mostly here today, which is a graphic user interface tool to run acoustic simulations and do acoustic design work. And on the other hand, we have the SDK product, which is a programmatic interface to Treble's core simulation technology, which means that you can take our simulation technology and plug it into your own platforms, your custom R&D workflows, and so on. I'll briefly explain each component, and then I'll go into the demoing of the new features for the simulation suite. So our core sound simulation engine comprises two algorithms or two methods for simulating acoustics. For high-frequency modeling, we use what's called geometrical acoustics, which has sort of been the industry standard approach for doing room acoustic simulations for quite some time. Whereas for low frequencies, or low to mid frequencies, we offer wave-based simulations. Wave-based methods are inherently very accurate. They capture wave phenomena such as diffraction and interference and phase and things like that very well. The reason, and these phenomena typically happen more in the low frequency range, so a very natural approach is to combine geometrical acoustics, which is sort of a high frequency approximation at high frequencies, and then wave-based methods for low and mid frequencies. This way you get sort of very high accuracy, but also at fast computation speeds. That's the core tech. We of course have a ton of information on our website and validation cases and so on if you want to dig deeper into what lies under the hood. The Acoustic Simulation Suite is this graphic user interface tool, which I'll be showing today and talking about new features and so on. This product can be used for various different things, some of which are shown here. The kind of initial target use case we had in mind when making this product is architectural acoustics or room acoustics design. Now there's also quite powerful capabilities for modeling sound systems in rooms, so you can not just be optimizing the space, but also the sound system in the room and the interplay between the two aspects. You can do outdoor sound simulations at sort of small to medium size scales, and we have very powerful listening or oralization capabilities as well, which allow you to kind of construct or design soundscapes. Now, what we are really trying to bring to the table with this product is essentially three things. First of all, better accuracy brought about through our very advanced simulation engine, which in turn hopefully reduces risk, increases confidence in the results, which in turn hopefully increases the overall quality of your designs, avoids over-design and things like that. Secondly, we're really emphasizing to make the whole workflow of doing acoustics design as seamless and efficient as possible. This means, for example, the process of getting a 3D model into the tool to run simulations, the iterative workflow of optimizing your designs, collaborating with colleagues. The whole thing is web-based and cloud-based, which means that you can run it from any device, you can run several simulations simultaneously and things like that. So this is a very strong emphasis of ours. And third, last but not least, we're also improving oralizations, which is this notion of being able to listen to your simulation results. And here we're just trying to make them more immersive, more interactive, real-time, and more fun. This is what we're trying to bring to the table. You guys be the judge of whether we're successful or not, but this is our mission. Here is some very nice words from one of our users, Bradley Alexander from Bollinger and Grohmann. He has been a power user of the simulation suite for quite some time now, and he's commenting here that the speed, user-friendliness, and accuracy enables them to provide more simulation services and ultimately work more efficiently than they had been able to do before. Okay, I also want to spend just 1 minute talking about the SDK product, even though that's not sort of the topic of today's webinar. The SDK is a very powerful product which allows you to, as previously mentioned, plug our simulation technology into your own custom workflows. You can script against it and set up simulations in a scripted way as opposed to kind of with clicking through a graphic user interface. You can plug it into gaming engines or 3D modeling tools or whatever, really. Sort of the sky is the limit because it's an SDK product. You can do whatever you can think of with it. There are a few use cases we have in mind or have had in mind when making the SDK, even though the sort of sky is the limit, as I just mentioned. But for example, synthetic data generation, being able to set up thousands of different scenarios and simulate them all in the cloud and get back a big data set of audio data, which you can then use to train some kind of audio machine learning algorithm. Being able to run advanced acoustic simulations, such as full bandwidth wave-based simulations, ultra-high order ambisonics output, and there are some advanced features in the SDK which have not yet at least found their way to the simulation suite. Integrating it into third-party tools, as previously mentioned, and being able to do, for example, parametric sweeps, where you, let's say, automatically vary absorption in a room across some range, and then you kind of have the whole thing simulated through the SDK and get back kind of an optimal result or something like that. We launched this product about maybe 1 or 2 months ago. We have been rolling it out in a sort of, let's say, controlled fashion because there's a lot of interest in this product, but we want to ensure that that the first users get a good experience. So we have had a waiting list that people sign up to if they're interested in using this product. And this has been going really well, and now soon, probably already in January, we will start rolling it out at a more sort of, at a faster pace, let's say. So stay tuned for that, and please sign up for the waiting list if you're interested in trying this. A key notion of the SDK, and actually of all Treble's offering, is the cloud-based nature of the product or the platform, which allows you to really run many simulations simultaneously, accelerate heavy wave simulations a lot, so they actually become kind of practical to do or within practical runtimes. Collaborate with colleagues, that's something I'll be talking about quite a lot today, and so on and so forth. And indeed, especially if you think about use cases like data generation, where you need to be able to run hundreds of simulations within a short time. Here is Trausti Þormundsson, who is Director of Audio Hardware at Google, noting that the simulation technology Treble offers is solving some of the toughest problems that they are facing, and the timing is good for them. So that's very nice. Thank you for that, Trausti. Anyway, that was my brief intro. Let's now move on to the main thing for my part, at least here today, which is the new features that I want to demo in the simulation suite. There are sort of 4 main categories of features that I will be demoing. First, improved or extended features for importing geometry into Treble. Up until now, you have needed SketchUp to work with the Treble Simulation Suite, and we have a very nice plugin in the SketchUp tool, which kind of speaks with the Treble Simulation Suite in a very nice way, and allows for a very iterative and nice, or let's say an efficient iterative workflow between the 2 tools. But not everyone wants to work with SketchUp, so now we are introducing the capabilities of importing geometry from a wide variety of other tools, and I'll show you how that works. Second, which is not less exciting, is the collaborative features, or as I say, unleashing the power of the cloud. which means that we can really start exploiting the cloud-based or the web-based nature of the tool to make the whole collaborative workflow better. This includes being able to create listening experiences in Treble or oralizations and then share them via the web with just one click of a button to any external collaborator who can then, on the other side, listen to your design options and so on. I'll, of course, demo this in a second. And then also so this is kind of sharing and working with external collaborators, but then also internally working with your within your organization, you can have shared databases of materials and sound sources, loudspeakers, shared projects where people can be working together on the same project in kind of a Google Docs style approach, and overall just trying to improve the whole workflow of doing acoustics. Third part is improved loudspeaker modeling techniques. So in the last webinar, we showed a bunch of new features for modeling sound systems in Treble, and we have just taken that a step further now, and I'll demo that. And then fourth, last but not least, our anechoic sound library is growing fast these days. We've been running some measurements campaign in the anechoic chamber. That's been a lot of fun, taking in all kinds of sound sources and instruments and so on into the chamber and recording them. And I'll show a demo of this, what we've been adding to the tool. So I think now I will just go over to the simulation suite and start the first demo, which is the geometry import part. All right, here is the Treble simulation suite, accessed through app.treble.tech. Now I want to get some geometries into Treble. I can, of course, use the good old SketchUp plugin and that workflow, but it so happens now that I have some 3D files in another format than the SketchUp format, which I want to get in. So you will see here is a new button called Import Geometry. It says beta because it's been in beta with some select testers for a while now, but will be made available to everyone next week. And let me just go ahead and import or try this. So as you can see here, we support DXF, OBJ, and 3DM file formats. Most, if not all, CAD modeling tools are able to export into at least one of these formats. And I'm going to import a DXF file, which I have lying around here on my computer, like so. And first, let me just start the importing. It takes a few seconds to run because it's shipped to the cloud. There is some processing that takes place on the geometry, both checking that everything's okay and even trying to automatically fix it if there are some small issues with it. And indeed, this is going to happen for this model. I happen to know that kind of beforehand. So let me show you here while it's importing. This is the model. It's from a round-robin study. And you will see here, if I zoom in here, it has some small holes or gaps in the model. It's not perfectly sewn up, so it's not technically watertight. But the Treble geometry processing algorithm, which sits in the cloud, will analyze the model and actually is able, in this case, to fix the model for us and make it completely watertight. That means that we can use both the geometrical acoustic solver and the wave-based solver. The wave-based solver needs a watertight model to be able to run the model. So once this is done, we will get some feedback on the geometry, and it will tell us whether we need to improve something or whether there are some errors or something like that, and then we can move forward. It says here, the feedback, the wave-based solver is enabled, so that means that the model is watertight, so it was fixed by this small slit there as an example was fixed by the geometry processing. It does give me some warnings, which oftentimes we can just ignore, but let's at least read them. It says here, potential small gaps between faces or edges detected. Small gaps between two elements can impact the speed of the wave solver. Likewise, short edges detected. Consider simplifying your geometry. Short edges can impact the speed of the wave solver. So there's nothing wrong with this model. It will run just fine and very accurately, but perhaps there is some room for improvement of improving the geometry to kind of make the wave solver a bit more efficient. We can take this into consideration. Generally speaking, we want maybe details down to 5 centimeters range, something like that in our models. But I'm just going to go ahead and ignore this, at least for now, and see how it looks. So I click next here, give it a name. Let's say RR3 testing import project. I'll create a new project, webinar import, and new space, RR3, something like this. Okay, here is the model we just imported. I'm just going to quickly open it up. We see it here. It's been imported successfully. We see, for example, this slit that we had there in the original file has been sewn up or fixed. So the model is now watertight, and we can run both the wave solver and the geometrical acoustic solver. I'm very quickly just going to create a simulation here. Assign some nonsense material on everything just for the sake of setting up some simulation to show you how the estimate functionality looks and whether we actually need to consider simplifying the model even further. Throw in sound source and a receiver, and now it is proposing that I simulate up to 450 Hertz. Let's maybe see, push it a bit higher, up to 700 Hertz. And then I will mesh this. When I click the estimate button, what happens under the hood is that the model is being meshed, which is sort of a pre-processing step for being able to run the wave simulation. And from this, the software can indicate how fast the simulation will be. And if we look at this model, I think it looks quite okay. So maybe no need for further simplification. There are some geometric details here which are quite small. See, for example, this edge here. So maybe this detail here could be simplified. This would speed up the simulation a bit. But then again, if we're willing to wait maybe just a few more minutes for the simulation, then this is also just fine. So here it's saying the simulation up to 710 Hertz takes 9 minutes to run. I think that's quite acceptable for a wave simulation of this size room. It's around 360 cubic meters. So this is actually just fine. But as mentioned, we could maybe get it down to 5 minutes or something like that if we really wanted to optimize for speed. But this is quite okay. And then I could just hit the run button and run the simulation. Okay, I wanted to show you a different example, importing another room. So I'll go back here where, so let's go again. This time I'm going to import a little bit bigger room. This is from the benchmark for room acoustic simulations database, so a public database of benchmarks for room acoustic simulations, as the name implies. This is a bigger space, and I happen to know for a fact that this is even less perfect of a model than the one before. So here, the geometry checking service will attempt, or the geometry processing will attempt to fix the model. And that's what's going on right now while we wait. But I know for a fact that it's not going to be able in this case to completely fix the model. So there will be some watertight or sort of slits or gaps which was not able to be fixed. But that in turn means that we can still run the simulation, but only using the geometrical acoustic solver. So now we have kind of two options. We can either go back to the CAD modeling tool and improve the model such that we can run the wave simulation, or we can just accept it as is and run a GA-only simulation. And in many cases, that is just fine, especially if we're running a project which is sort of, let's say, time critical. So Treble certainly accepts anything ranging from, quite imperfect models all the way up to more perfect models. Here we see a couple of warnings, not watertight, so it will tell me only geometrical acoustics. That's fine. And 03, import, something like this. And now this shows up over here. It has a little purple guy here, which tells me not able to run a wave simulation, but GA is just fine. And here we see this quite complex model successfully imported. And that's it for new geometry import capabilities. If your model has some issues, let's say small short edges or not watertight or slits or something like that, then you can also very soon we'll add the capability of the tool showing you where in the model you have issues and so on. So that will come probably in as early as January, this kind of feedback mechanism. Okay, that was demo number 1, geometry import. Let's next move to the collaborative features. the first collaborative feature I want to demo is a really exciting one, which is the ability to create shareable oralizations. So you can set up your own oralizations, and then with kind of just one click of a button, you can send this oralization to anyone, anywhere in the world through the web, and they can on the receiving end step into that oralization through the browser and listen and experience this. This can, for example, be a very nice option if you're an acoustics designer and you want to share some design options with, say, a client. And this helps them kind of make an informed decision of which way to go. So I have a model here, an open plan office, which I will play around with to demo this particular thing. I've set up a simulation here where I have 2 sound sources in the space, 3 receivers. I ran it with some particular material configurations. I'm going to set up an oralization here, and I'm going to compare these 3 simulations that I've run, which are sort of 3 design options for my client, let's say. First one is with a hard ceiling, so quite reverberant space. Then I've added an acoustic ceiling, and then I've added an acoustic ceiling and some partitions between the desks. And I'm going to put in a couple of sounds here for the sound sources that are in the simulation. So let's say Office Atmos and Office Dialogue. I will sort of tune these things a bit here. Maybe we can quickly listen before I share it. So this is the dry sound, the anechoic sound before going into the room. And now I jump into the room. Maybe minimize this guy here so we see a bit better. Different options here. Jump between different receivers. Okay, I'm quite happy with this oralization that I've set up. So now I want to share this with my external collaborator. So I will save it as a preset here. I'll give it a name, webinar sharing test 1, and I'll write a short description. Option, let's just say A, recommended, or whatever, acoustic ceiling plus partitions. B, cheaper option, acoustic ceiling only. C, hard ceiling, current design, as an example. Something like this. Save this bad boy and then share it. So now I can either just click this button and get a link that I could share with my collaborator, or I can input an email. I'll just send this here to myself, to my private email, as such. Now I will receive a link via mail, which I can open up as an external collaborator. I don't have a Treble account or I'm a Treble subscriber or anything like that. I'm just somebody who got an email. Let's go here. Here's the email I received. Let's take a look. So it will send me to this sort of standalone oralizer. First I'll get some tips on, or let's say a small tutorial on how to use it. I'm a person who has maybe never used this oralizer functionality before. It tells me here I can flip between different design options. I can change listening positions by clicking the arrows or selecting from the drop-down. I can look around by panning the mouse with the right button. And I can play with the play button. So this is kind of what faces me. Here is the description I wrote, so I can see, okay, A corresponds to the recommended design, B is the cheaper option, and C is sort of where as it is today. And I can simply hit the play button. I can experience this here, compare how it sounds. It's kind of improved acoustics versus the current state. So that's a new and very powerful way to share oralizations with your clients and external collaborators. Okay. Okay, speaking of collaborations, this was kind of external collaboration, but also collaborating within your own organization. we have the ability now to have a shared material database, which can be very useful for big organizations or small and big organizations, and also shared sound source libraries as well. So if I just show you here how the material library looks now. So we see here that we have 3 different tags of materials or categorizations. We have the default materials, which are the materials that come with Treble. But then we also have materials that belong to my organization, that my user is associated with. And this is the Treble or fictional organization, and we have made some materials here which belong to that organization. I can also see materials that I have myself made, and I can then choose whether to share this material with my fellow colleagues or not. So maybe if I'm just testing something, I would not do that, but if I've input some new product, for example, into Treble, and all of my colleagues want to use that, might want to use that, then I can kind of commit this to the shared material library. And we can do this here. If I go to the detail view of this particular material, then we can, click and unclick this share with organization capability. The same goes for loudspeakers or sound sources. So if I open the loudspeaker database here, then we see all the different loudspeaker types that are in Treble now. This list is constantly growing, but then again we have this categorization as well, where we have some kind of loudspeakers that have been imported and shared within my own organization, including some loudspeakers that I have myself imported, and then again I can choose to either share this with my colleagues or not. That was materials and loudspeakers. This is already live for users. What's coming very soon is then also being able to share projects within an organization, so you can kind of colleagues be working on the same project together. Let me show you that. All right, so the sharing of materials and directivities or sound sources is already live for users. The sharing of projects and kind of being collaboratively able to work on the same project or the same space is something that we will push live as early as January next year, but it's being worked on these days. This is sort of how it will look. So here you can see some different projects that I've been playing around with, and you can see that some of these spaces have different people associated with or different users associated with the spaces, meaning that they have collaborative access to this particular space. And I can then add and remove, or at least add users here from my perspective, and an administrative user can also remove people from spaces. Let me show you how that can look. So I can go into the model here, manage members. Here comes a list of the people who are sort of on my organization. I can add users as I want, as so, and that's basically it. Now they are associated with the project as well, and can kind of go in and modify and run simulations and so on. That was collaborative features, sharing organizations with external collaborators, sharing internally materials, directivities, and projects, and being able to work on them together. Next thing I wanted to show you is improved capabilities for loudspeaker modeling. So in the last webinar, we introduced the abilities to import CLF files into Treble, so you could import your own loudspeakers, and as well sort of have a big database of loudspeakers that come with the tool. This database is also growing rapidly. We're working with many of the big loudspeaker manufacturers to get more and more data into Treble. But we're adding more capabilities now. Let me showcase that quickly through a demo. So let me show you this little example space here. It's a sort of a little home studio. Let me hide this surface receiver here so we see a bit better what's going on. So here you will see a small home studio or listening room where I have a couple of Genelec speakers here, left and right, and a D&B subwoofer here on the floor. And before, we could model the directivity of these sources, but now we can also take into account their frequency responses, and we can EQ the sound power of the sources as well, and kind of different frequencies. And I've already run a couple of simulations here. Let me just show you real quick how this can look like. So here, now this frequency response of the speaker is also taken into account, not just directivity, and I could EQ the source if I wanted beforehand. And in fact, I did that here for For the sub, I did not EQ it, but I just adjusted the level to be a bit more reasonable, so the whole thing makes a bit more sense. And obviously the frequency response of the sub is taken into account as well. And I've already run a couple of simulations here, one with some acoustic treatment in the space and one without. And I think we can now just quickly hear what this sounds like. So let me go in here and compare these two simulations. I'm going to put some music on the different tracks. I'm going to load some sounds that I have here myself. So this is a Fleetwood Mac song that I'm going to put on. I'm putting the kind of left and right channel of each song or of the song on each loudspeaker, and then I'll put the mono track into the sub as well, like so. And then we can basically hear how this particular sound system, these speakers are going to sound in that room and experience that playing back this song. This is just the song, no room involved. And then if we go into the room, maybe the sub is slightly too high, so I'll decrease it a bit. Then I can compare. Without the acoustic treatment, the room is obviously more reverberant. Just the sub. Can hear without the sub. And then we could of course use Treble to optimize this whole thing, optimize the acoustics of the room, optimize the position of the subwoofer or the loudspeakers, optimize what type of loudspeakers we would prefer to have in the room, and so on and so forth. Either via auralization or of course looking at graphs and numbers, frequency responses, color maps, and so on and so forth. That was the improved loudspeaker modeling. The last thing I want to show you is an update of our anechoic sound library. Let's go here into another model, which I've also set up a little fun simulation. Bigger space, an auditorium here, where I have placed sound sources kind of at different positions on the stage, and then a few receivers throughout the space, kind of one here on the stage, and then kind of front row, sort of third row, 11th row, and I think this is 16th row. And the anechoic sound library is quite big already, or has been quite big, but now we have added around 150 sounds more to it. So if we go into the auralizer here and look at the library, then we've sort of added some categorization of sounds in here. We've added search functionality as well, and including, some of the sounds that we have added is, for example, all kinds of noise signals that can be useful for analyzing the sound system or the room. We've added a lot of music, Icelandic choirs, funk music, pop music, and so on, all kinds of instruments playing, ranging from synthesizers to cellos and everything in between. We've added all kinds of sort of soundscape sounds, whether that's a blender or a cough or a coffee machine or steps, ventilator, kind of to model HVAC systems. And so on. So all kinds of speech as well, various different languages, English, Mandarin, Danish, Greek, Spanish, so all kinds of different sounds. And just for fun, I thought I would take this little auralization setup or the simulation setup. So here we can put kind of different so all these funk tracks here are kind of belonging to the same musical track, so we can put kind of different tracks of that song onto the different sources and kind of hear like it would be in this room. So I'll put the bass on the source I called bass, and second guitar here, something like so. So now it's like one guitar amplifier is here, the drum kit is here, the bass amp is here, and the other guitar amp is here. And we can hear this with kind of different acoustic conditions in the space. Maybe we should first just listen to the dry track. It sounds something like this. And now let's go into the room, first on the stage. Yeah, that was an example of some of the new sounds, but as mentioned, a whole lot of new sounds for you guys to play around with when creating organizations. That was it for my new features demos. Hope you liked it. Of course, you can expect more things coming up. Already in January, we will have another webinar where we will be showing some quite groundbreaking functionality of getting BIM models into Treble, including automatic geometry simplification and space picking within a complex large BIM model. Very much looking forward to show you that. And then certainly in the new year, more things will be coming very soon. So thanks for listening to my part. Let's now switch over to Ólafur and hear his presentation and then do the Q&A.
Hello all and welcome to this short presentation on acoustical simulations of small rooms in Treble. I'd like to start by introducing myself. My name is Ólafur. I'm an acoustical engineer and I work as a consultant here in Reykjavik and have been working as such for what's coming up on 8 years now soon. I mainly deal in the fields of room and structural acoustics, but my main area of interest is actually room acoustics and more specifically room acoustical simulations. But working in a small market like Iceland, you have to be a jack of all trades if you want to stay employed. But I have been working in and with Treble for what's coming up for 2 or 3 years now. And what I'd like to present to you today is the first case study I did when I started working in the software. The study in question is of this room here, and this is actually my own office. And the reason I chose this room for the study is that this is a very small room. And like many of you, the main opportunity I saw when I started working with Treble was to be able to accurately simulate the sound field at low frequencies, or more specifically in the frequency range where the modal behavior is dominant. So this being my office has a few advantages. Firstly, I can obviously do acoustic measurements whenever I want, at least when my neighbors are not at their own office next to me. And this being a small room is very relevant for Treble strengths. You can see the key fact about the room here, the room sizes in all the major dimensions. The room has a Schrödinger's frequency of around 190 Hz, that is, the frequency below which the modal behavior is theoretically dominant. Now, when I've been working with geometrical software or geometrical acoustical software, what I've usually started with is by calculating the Schrödinger's frequency and multiplying it by a factor of, let's say, 2 or 3 or even 4 in some cases. I've estimated the frequency below which I do not usually trust geometrical solutions. Now, in this case, the Schrödinger's frequency being around 200 Hz would mean that I would never simulate this room using only geometrical methods. And therefore, being able to do this in Treble is very tempting. Another interesting fact about this room is what you can see in the picture here on the right. And that is the fact that the acoustical treatment in the room is in the form of porous absorbers that are lined along the perimeters of the ceiling. So theoretically, we should get better low-frequency absorption with this placement, where all the modes have their pressure tops, than if the same area of acoustical treatment would have been placed in the middle of the ceiling. So this is another fact that I wanted to explore when I started working in Treble, if it could accurately simulate this case. So this is the room I've modeled, and now I'd like to go over to Treble software to show you how it looks like there. Let us see. So here you can see what I've modeled in Treble. And if you compare this to the pictures I showed you earlier, you can see that I've modeled all the main features of the geometry. I have the printer and the desk and even the PC monitors and the chairs modeled as chairs, the PC towers and the windows modeled as indentations into the wall as they are in real life. So when I went into this project, this is obviously my own office, so I know the target reverberation times, for example. What I didn't want to do was to create something in Treble and then just meddling around with the material solver until I found something that would fit with the measurement. I wanted to see if I could take the predefined materials within Treble and see if they could give me a good solution that would be similar to the measured response. So all the materials defined in this model come from Treble's material database. And you can see that the three perimeter walls here are made out of gypsum. There is a wooden door here with a wooden board over it and a window and another gypsum wall. The outer wall here is made out of concrete. You can see the the absorption coefficients rather here on the bottom. The floor is made out of, it's a concrete floor with a linoleum covering over it. This area of the ceiling is just made out of smooth painted concrete, and the perimeter, as I said, is made out of 50mm rock wool panels. And I chose the rock wool panels in Treble that gave the most similar absorption coefficients to the data provided by the manufacturer. Now for other parts of the interior, for the chairs, I chose theater seating within Treble. I found that to be agreeable, the absorption coefficients that is. I model the printer and the monitors and everything that's made out of plastic, but the only thing in Treble I found that is plastic chairs in that case, but the approximation is close enough. Now for the table, I chose, as you can see here, a material that is defined as wood. So I would say for a hard lacquered table like this is, for the low frequencies, this is a close enough approximation, but the, let me see here, sorry, but the absorption at 500 Hz and above is a bit high for a completely hard table. But in this case, we actually have some papers and books and things like that on the table itself. So therefore, I found this approximation to be quite agreeable. And then the final approximation is for the shelf. So for the parts of the shelf that are filled with books and folders and loose papers, I again chose this wood material that has a bit higher high frequency absorption than the base wood itself. But I would even say that in this case, since these shelves are filled with books, that we are actually underestimating the absorption at 500 Hz and above a bit. And keep that in mind when we look at the final results at the end. For the parts of the shelf that are hard, like the sides that have nothing on them, they are just hard lacquered wood, I chose this material here, 50mm thick wood, which has a very flat curve over the whole frequency range. Now, to go back into the slides, I will show you here another interesting fact. So the first thing I did after I modeled the room in Treble was to measure the frequency response in the room and compare that to the simulated frequency response. Now there's a caveat to this before I show you the comparison graph. I would have liked to normalize the results with regards to the direct sound coming from the speaker. But I have not had the chance to go into an anechoic chamber to do that. So just know that the source defined in Treble is a theoretically perfect source with a completely flat curve over the 1/3 octave bands, whereas the loudspeaker that I used in real life is not flat at all. It has, for example, based on my rough testing, 25 to 30 dB more power in the 200 Hz range than in the 30 to 50 Hz range. And the range I'm going to show you is from 30 Hz up from 200 Hz, or up to rather. But what this comparison is at least good for is to compare the location of the modes in the frequency domain to see if treble manages to accurately predict where in the frequency domain the modes will land. So this is the first case. I placed a source in a corner and a receiver in another corner to excite all the modes and to be able to measure at the pressure peak. And you can see that the results are quite agreeable. Of course, as I say, the measured response drifts upwards since it has more power at higher frequencies. But this at least gives you a good approximation of how the modal response is in this room. And so for another case, I set up a simulation and a measurement with the source at another corner and the receiver at yet another corner, and then I got this. And this is even better, I think. So the response of my loudspeaker is quite flat between 30 and 50 Hz based on my rough testing. So we can see that the amplitude in those cases are quite close between the simulated and the measured response. And the modal behavior is also quite similar. Now, what this means is, of course, that being able to start finalized design early on in the design phase comes with great opportunities. The most obvious cases being in the acoustical designs of studios and recording rooms and rooms for music. And I can name you just one experience that I've had where the old approach, where what I've done usually is that I've designed the acoustics in a rough manner, so I've placed the absorption in the ceiling and the wall absorption, and then I've said in my reports that the final design will have to be finalized based on measurements at the end. So when I had the project working for a municipality that was designing a music room, we put in these caveats, but projects like this, they always go over budget. So what happened in that case, that even though we specified that there were some acoustic measurements that had to be made at the end to finalize the placement and design of bass traps and Helmholtz resonators and things like that, well, when the building was ready, the money was out. So we didn't get the chance to go and do a measurement until 2 years later. And it's been 2 years since that measurement and they still haven't installed our design. So had we been able to finalize the design in the design stage itself, it's much higher chance that we would have gotten our design goals through in the final project. And an interesting fact about this also is, this is a small room, a small shoebox-shaped room. So you could theoretically just calculate the room modes yourself using more simple methods. But the amplitude of the response seems to be also accurate. So that means that, for example, the third mode that you can see here is actually a tangential mode. And if I had to design this based on my intuition, I would assume that the tangential modes would contain less energy than the axial modes. But then in this case, we can actually see that this mode is quite dominant. So you have to make sure you treat that very carefully. This is something that you would not be able to predict in the same manner unless you do measurements at the end. Now, what I would like to show you next are comparisons of the reverberation time in the room. What you can see here is an average of around 15 measurements within the room for different source and receiver positions. The red dashed line shows you the mean or the average of all those measurements. And the highlighted area, the golden highlighted area, shows you one standard deviation above and below each measurement. So ideally, we would like our simulation to fall within the highlighted range. So first of all, I'm actually going to compare the measurement to using Sabine's equation. So what I did is I took all the surface area in the model itself that I had modeled into Treble. I took that, placed the same absorption coefficient as I did in Treble, and calculated the Sabine result. And you can see that Sabine overshoots the measured response or results by around 25 to 40%. But the curve, the shape of the curve, follows that of the measured result. So I would like to add the caveat, as I mentioned earlier, that the absorption coefficients for the shelves at 500 Hz and above are underestimated, as I said, so keep that in mind. But still, it's clear that Sabine does not give us accurate results. Even though I'd say as far as using Sabine in small room goes, with its inherent problems and non-diffuse sound fields, or in non-diffuse sound fields in general, this room is probably as good as it gets for Sabine in small rooms. And the reason I say that is that the acoustical treatment does not cover the whole ceiling, so we don't have an extremely dominant sound field in the horizontal directions compared to the vertical ones. The geometry is also rather simple. There's no coupled spaces or anything like that. And we don't have any wall absorbers that Sabine would probably underestimate the effect of. But that is not to discredit Sabine. I mean, the simple checks are there for a reason. And this is obviously a very powerful indicator of the final result. So the next thing I want to compare this to is using Treble, but only the geometrical algorithm. So only the ray tracing part, no wave solver. And there you can see what that gives us. So this is wildly off and is a reason for, as I mentioned earlier on in the presentation, why I would never use a ray tracing algorithm for a room like this. This is with every material defined by default in Treble and with the default scattering coefficients. So what I did then was to try and increase the scattering coefficients where I found it relevant. For example, on the shelves, on the table, the ceiling lights, and things like that. So by increasing the scattering coefficient by a modest amount, we get a result like this. And what actually happens, not shown here, is as you increase the scattering in the room more and more, you get a more diffuse sound field, and the ray tracing algorithm approaches the result of Sabine's equation. But now the main interest is, what does the wave solver give us? And here you can see that. And you can see these blended results down in the 125 and 250 Hz frequency range. And again, at 500 Hz and 1000 Hz, we are basically one standard deviation above the mean. But as I've already mentioned twice now, I am underestimating the absorption coefficients in these frequency bands or octave bands. And on the shelves, I'm doing that knowingly, so keep that in mind. I think these results are quite great, and being able to accurately predict the reverberation time at low frequencies like this in this tiny room was a complete revelation when I first started working in Treble. So I have and did these measurements with a new sound level meter, and I couldn't figure out how to extract the energy decay curves themselves from the meter. But what we can do is we can try to deduce how they look like by comparing different parameters. So the first thing I did was to compare the measured T20 reverberation time to the measured T30 reverberation time to see if the curve is doubly sloped, or at least if there is a change in the slope in the -25 to -35 dB range. And this is a comparison of measurements, as I say. So on the left we have the measured T20, and on the right the blue bar shows the measured T30, and we can see that there's not really a great difference. So then the question is the same true for Treble? What does happen if we compare the simulated T20 to the simulated T30? And the same thing goes there. There's not really a big change between the two. Obviously we have this change between the measured values and the simulated values above in the 500 and 1000 Hz octave bands, but I've already gone into that. So the next thing to compare is the early decay time, or the EDT. Now that comparison is rather more tricky, since EDT is rather spatially dependent. So it depends quite heavily both on the location of the source and the receiver. But this can at least give us some indication by moving things around in the room, does treble and the measured response follow each other. So here we can see the case where we have the source in the upper right corner, highlighted by the green 1, and the receiver in the lower right corner, highlighted by the blue 2. So in my measurements that I made, the source was actually closer to the corner itself, but in treble you can't place a source next up to a surface. So bear that in mind. But what I wanted to see was then if I move the source and the receiver around, is the behavior of the curves similar between the measured and the simulated response. And here we can see that for another location of source and receiver, we have the source now at location 3 and the receiver at location 4. The overall trend in those graphs is quite similar. Now, to show you or highlight how spatially dependent this is and how tricky this comparison is, and this is basically just a rough guide, I have here yet another case. Here I have the source at position 2 and the receiver at position 3. And you can see that at, for example, 500 Hz, the difference is around 20%. Now, I will say that when I made the measurements, I didn't measure exactly the distance to the nearest walls or surfaces. So when I put the sources and receivers into treble, I was basically eyeballing it. And this is important to keep in mind because I would now like to show you the results within treble itself and what we can see there. And here we have a bunch of surface receivers that I've defined within the model itself. Here we have the simulation, and here we have the source that I just showed you, which had this difference, for example, this 20% difference in the 500 Hz frequency band. And if you go, I've selected early decay time, I will select 500 Hz, and I will select approximately the location of the receiver, and you can see it's around 0.43, similar to what I got in the simulated response. But if I move it just a tiny bit, now I get something closer to 0.5, which is actually the measured response. So you can see how extremely spatially dependent this variable is. But since I am here in the results view now, I'd like to show you a little bit how I use the results within treble. So what I usually do is that I always define this surface receiver grid, but I also define multiple receivers and sources within the room itself, as you can see here. The reason I do that is so that I can go into the report view, select my source, and then use the multi-select function to select all the receivers in the room. And by doing that, I can get the average response over the whole room. So if I would like to compare, for example, this simulation using the wave equation up to 1000 Hz to a simulation using only the ray tracing algorithm, I can do the same for the ray tracing algorithm. And now I've got a good estimate of the difference over the whole room just by looking at the bar graph here, since I'm using the average of all receiver points. Now, you can also use this grid response to your advantage. So what I would like to show you next is, as I mentioned, one area of interest to me was to see the effect of placing the absorption along the perimeter. So it actually works out in the model that the perimeter here, where we have the absorption, works out to be around 9 square meters. And the center of the ceiling, where we have concrete, is also around 9 square meters. So by switching around and placing the absorption in the middle and keeping the perimeter, or defining the perimeter as being made out of concrete, we are actually not changing the absorption area in the room itself. We are only changing the location. And what we can do is that we can go into this defined grid of surface receivers, look at the T20 at 125 Hz, where this is most relevant, compare this to what I've designed here as, I've defined this as a reverse ceiling. So this is the case with the perimeter being made out of concrete and the center being made out of a porous absorber. And you can see that there's quite a great difference here, but you can also see that the legend here is not the same between the two cases. But you can actually double click on the legend at the highest point and at the lowest point. And now we've gotten the same legend between the two simulations. And you can see quite graphically the difference it makes to place the absorption along the perimeter. Just looking at the heat map, you can see this quite extreme difference of 0.3, 0.4 seconds at 125 Hertz. Or we could also look at this again in the bar graph and see just how much of a difference this makes. So the final point I wanted to touch on before I end this presentation is the level of detail necessary to model in each case. So what I usually do when working in Treble is, first of all, I think, how high am I going to take the wave solver? And in this case, I'm taking it up to 1000 Hertz, which is basically as high as I go, usually. And then I think, well, what is the wavelength of a wave that has 1000 Hertz frequency? That's around 34 centimeters, so a quarter wavelength is around between 8 and 9 centimeters. So I usually, and this is just my intuition, I then don't model any object that are smaller than 10 centimeters in 1 or 2 dimensions, generally speaking. Because of course, the geometrical modeling is often what takes the most time, and being able to save time can be quite critical when you're working with a lot of rooms and are pressed for time. Of course, if you want to increase the detail, there can be exceptions, of course. I'm just speaking from my own intuition and experience so far working with Treble. We also know that the minimum distance between surfaces is 5 centimeters based on Treble guidelines. Any smaller distances than that can cause mesh errors, so keep that in mind. But what I really wanted to highlight is the modeling of the boundary of the room. So one thing about Treble is that you cannot place two parallel surfaces on top of each other. For example, if you place a shelf on a wall, you have to cut a hole in the wall where the shelf comes, or the shelf is placed. And then you actually have to cut a hole in the back of the shelf as well. So if you look at the room from the outside, it looks like an indentation into the room itself. And you can see that being highlighted in this model here. So this is the model that I've been showing you. And you can see how I modeled the shelf in this case. I just modeled the complete shelf and placed it 5 centimeters from the surface or from the back wall here. Whereas in real life, it's more like 1 or 2 centimeters away from the surface. So I had an alternate option. I could have modeled it like this, so like an indentation into the room itself. And this is actually quicker and simpler to do. So the question is this accurate? And I would theorize that this can cause some errors. So first of all, what happens is that by doing this, we are removing the low frequency absorption that the gypsum wall gives us, because I have not changed the definition of the front of the shelf between the two simulations. So we will actually get higher reverberation time in the low frequency range. And I can show you this now on the graph here, where I compare the simulated and measured responses. And you can see here that for the simplified geometry, all the coefficients are the same. The geometry has just been simplified. We get much higher reverberation time in the low frequency range compared to that of both the measured and the simulated case with more complete boundary modeling. And if we go back into Treble and look at this case there, we can actually think about, well, the logical next question would be, what if you just create a hybrid material for the front of the shelf that has the low frequency absorption characteristics of the gypsum wall and the high frequency characteristics of the shelf? Well, the problem with doing that in a model like this is that by doing that, you have you have changed the location of the boundary and moved it into the room according to the depth of the shelf itself. So in this case, we have a 40 centimeter deep shelf and a 4 meter wide wall. So essentially what you've done is you have reduced this dimension by 10%. But think about what the wave itself, the low frequency wave, will see. It will not be affected much by a 1 centimeter thick shelf, but it will be affected by the gypsum wall behind it. So you or what I found, and again, this is just, I'm not the complete authority on the matter, this is just my intuition. But I found that making simplifications in the boundaries can lead to quite some errors. So I would suggest that always put yourself in the frame of mind of what wavelengths you're dealing with. Think about the quarter wavelength, think about what will affect the wave, especially when it comes to the boundary, if the boundary is rigid or non-rigid, and really try to create an accurate skeleton of the room itself in order to get a good simulation approach or result in the end. So I think I'll leave it at that, and hopefully we'll get some interesting discussion after this. Thank you very much.
Okay, that was it for the presentations. Thank you, Ólafur, for being with us here today.
Thank you for having me.
I really enjoyed watching you use Treble and seeing some very interesting results, some good results, I feel, especially from the wave solver.
Yeah.
That was fantastic.
Yeah, I quite agree. The low frequency simulations turned out to be rather excellent.
Yeah, indeed. That's good. We've gotten a few very interesting questions sent. By the way, below the video on the website, there is kind of a questions or Q&A field. So if you want to shoot in your question, there's still time. So just feel free to do that. But let's start going through the questions here. So the first question is, will we at Treble release plugins for other 3D modeling tools like Rhino and Revit? So right now, for geometry import into Treble, we have these kind of two options. On the one hand, the SketchUp plugin, which sort of live links SketchUp with Treble and allows for a rather, let's say, seamless workflow or iterative workflow between the two tools. And on the other hand, what we just introduced here today is the ability to import models from DXF and OBJ and things like that. So yes, that was a bit of a long intro. The answer is yes, we will be launching plugins both into Rhino and Revit. Rhino will come first, sometime early to mid to 2024. Revit comes a bit later because that's sort of a bit of a more complicated beast, but we're working really hard on that and will in January kind of introduce the first features towards this, which is not a plugin into Revit, but is the ability to import IFC files into Treble. So, yeah.
And I can actually add to that all my work has been done on a test branch of Rhino. I've done all my modeling in Rhino, and it has worked very well. And I prefer actually Rhino to SketchUp because of the more powerful drawing capabilities of Rhino. And also, if you want to extract metadata, you can use Grasshopper and things like that to easier get all the data you need.
Exactly. So we have actually had kind of a working prototype of a Rhino plugin for quite some time, but we sort of just need to finalize the UI and then push it to the rest of the world. All right, next question here. Are there experiences with importing 3D scans as models? Would love to use Treble for acoustic troubleshooting of existing scenarios. This is an excellent question, and my first comment is maybe that Treble is of course very well suited to model both kind of new designs that have not been built yet and for renovation purposes of existing models. But right now you will need, in such a case, you will need to draw up the model in a tool like SketchUp or Rhino. But we have done some experimentation where we have taken a phone and scanned a room with like a LiDAR scanner on an iPhone, and then gotten that into Treble. And this was actually kind of pleasantly surprising how seamless this was. There are some very powerful technologies on the market available that take such a model and simplify it and clean it up, so it's kind of not so much work to go from what's scanned by the phone and into getting it into Treble. So this is definitely something that we will emphasize in our development efforts to kind of make this possible. I think it opens up a lot of exciting opportunities. Maybe Ólafur, you could comment a bit on sort of how you approach kind of renovation projects where you have existing spaces and there's a desire to improve the acoustics of that.
Yeah, I mean, how I approach the graphical approximation of the space, or just in general?
Maybe just in general, actually, yeah.
Yeah, so as I said, the first thing I always do is to think about the size of the room. And if it's a renovation project, then obviously I always start by doing measurements. And based on these measurements, I can then kind of get a good feel for what the Schrödinger's frequency is. So then I have some rough idea about the modal behavior of the room, or where the main modes will lie. And based on that, I decide how high I'm going to take the wave solver. So am I going to stop it at 250 Hertz or go up to 500 Hertz, or like in the room I showed you, 1000 Hertz. And based on this, I then think about into how much level of detail I will go. So this is all of what I do before I even start thinking about modeling. Because as I mentioned in the presentation, if you're only modeling it to 1000, or if you're modeling up to 1000 Hertz, then a quarter wavelength of 1000 Hertz is around 8 centimeters. And if you're modeling up to 500 Hertz, it's around 16 centimeters. So if you're mainly interested in the low frequency response in these smaller rooms, where I'm most inclined to use treble, then I tend to not go into much further detail with the geometry than what I absolutely require, because as you know, that's the most time-consuming part of any project, to model all the geometry in an accurate manner. So that's the first step. And then what I like to do is use the coefficients defined in treble as much as possibly can. And one of the reasons that I didn't go into in the presentation behind that is that what we're used to thinking about, the absorption coefficients, are just the tip of the iceberg. And they are more actually a geometrical data point than they are for the wave solver. So the wave solver needs more information regarding phase change and the rigidity of object, basically the impedance of all the surfaces and the objects within the room. And just speaking from my own experience, I am not used to thinking in that manner, at least not yet. I'm coming from the world of geometrical solvers. I'm just used to think about absorption and scattering. And then when I go and create my own material in treble and have to think about the rigidity and other things like that, I prefer to find something that's predefined in treble and to trust that, because I don't want to induce errors based on my approximations until I get more familiar and more comfortable with this mindset of impedance, basically, which we are obviously, for those of us who are used to working in acoustics, it's something we studied, but it's not something when you start working as an acoustician that you think about a lot, really. So the way I basically presented it here is then what I would do. I would try to use the absorption coefficients or the material defined in treble as much as possible and trust their definitions of the impedance, basically, and not play around too much with my own created materials unless where it's absolutely necessary. So that's kind of my mainline approach, I would say.
Interesting. Indeed, the materials in the material database from Treble have sort of been carefully thought out in terms of the impedance and not just the absorption.
Yeah.
And of course, by modeling surfaces in terms of the impedance, we model them much more precisely, especially in the lower frequency range.
Yeah, exactly. So that's what I usually do is, like in this case, I have the measurements. If I use the predefined material, how does that fit to the measurement? And in this case, it fits extremely well. So then I don't do anything else. If I have some major errors, then I would think about it. But in the cases I've worked on so far, I've never had any major problems. Or if I had some problems, then I would just change, for example, instead of a gypsum wall with mineral wool in the cavity, I chose a gypsum wall without mineral wool in the cavity. So sort of change the materials within the database itself very slightly. But when I've started and created my own materials, I mean, sometimes you have to do that if you have a Helmholtz resonator that you've designed yourself, then you obviously have to do it. But those are really the only cases, or the cases like that, where I am inclined to do that just from the beginning. Otherwise, it's more, for me at least, as a last resort, I would say. But that's just, as I say, my own intuition into this, and based on, I've done probably about 10 or 15 projects so far, and I've found the material database within Treble. If you look for the materials closely, it's actually pretty good. And you have a lot of options, for example, for rock wool and glass wool, a lot of different options of different thicknesses and different densities, and you can usually find something in there that's a good approximation of what you have.
Right. Very good. Final comment from my side is also that we will in 2024 be launching more features for importing materials into Treble.
Yeah.
So you don't just input absorption coefficients like you do now, but you can more like introduce some more precise characterization. Like this is a slotted panel with this level of perforations, and then you have this thick mineral wool behind which has these properties, blah blah blah, and sort of get accurately estimated impedance of this.
Yeah, so then I would be more inclined to use
maybe, yeah, exactly.
In those cases, yeah.
Very good. Thank you for that, Ólafur. Let's look at the next question. So, will Treble include internal sound insulation calculations of partitions? Absolutely. We are working on this very hard these days. Hopefully already in the first quarter of 2024, if all goes well, then we will launch this ability that you can have two spaces side by side and kind of simulate the sound transmission between spaces and create auralizations where you can hear, if a rock band is playing on the other side, how much do I hear here on my side? So, coming soon. Let's see. Additional questions. Is it possible to upload measured RT values to Treble and use them there? Not yet. Also something that's on our roadmap. What you can do now is you can quite easily export results from Treble either as an Excel sheet or just kind of copy the parameter values. There's a button there in the results view that allows you to do that, and then paste everything into Excel if you want to plot on the same plot measurements and simulations. I saw you did that in your presentation as an example. Yeah. But obviously we want to also make it possible to kind of do this kind of presentation within Treble. So this is something that's on our, I would say, short-term roadmap.
Yeah, and that has been, speaking for myself, main area of focus for me, because I have to write a lot of reports and make presentation to architects mainly, and they mainly deal with visualization. They understand everything better that they can see in front of them. So the more you can do within Treble without having to export or import, or export, that you can import into Treble and work in Treble, the better for the report work, I would say. So far you've come a long way, I think, especially with the surface receivers and the average that I showed, the multi-response function. And I would agree with the question that the next step would be then to import into Treble to be able to do everything within this.
Right.
Within the software.
Right, absolutely. Okay, we plow ahead with the good questions. Keep them coming. Here's another one. Are you guys working on showing multiple sources on the grid view? Speaking of grid or surface receivers.
Yeah.
Absolutely. This is something that we will, this is being worked on hard right now, just as the transmission, and something we will launch in early 2024. I guess, this will be a nice addition, being able to see.
Yeah, for every source position, basically.
Yeah, and so you see kind of multiple sources playing together. Yeah. If you have a sound system in a room, for example, and want to be able to model. Absolutely. Okay, here's a question for you, Ólafur, discussing the difference between the measured and simulated
frequency responses.
Yeah, exactly. And there was a kind of...
Yeah, there was a big... So if I go into that a bit, so the way I did the measurements was with the tools I had on hand. And I had as a source, I had an omnidirectional loudspeaker that we acousticians use to measure the reverberation time and the sound insulation. So the problem with using a speaker like this for a frequency measurement like this is that the response of a loudspeaker like this is very uneven. So as I said, the sound power output at 200 Hertz, based on my rough check, is around 25 or 30 dB higher than in the 30 or 50 Hertz range. So whereas in treble you have this perfect source, it is completely flat. Its power output is flat over the octave bands. So my real-life measurements will drift upwards with frequency since it just has much more power the higher up you go in the frequency range. So that's kind of a natural thing. Now to get a better comparison, I would have had to do, as I mentioned, normalize both results with regard to the direct sound. But I haven't had the chance to do that. So this was just a rough estimation to see if the modes would fall in the same frequency range, but you can't really infer too much from it. It was just a quick and dirty check, if I phrase it like that. So just to convince myself that I had the main mode at around 34, the first axial mode at around 34 Hertz, which I indeed did, and to see just if the modal responses were the same. And the agreement in that regard was close enough, and that is all you can really infer from a rough check like this.
Yeah, those were quite convincing results.
Yeah, and as I say, I mean, I would really like to get into. We actually have here in Iceland one anechoic chamber, I think, isn't that correct?
Yeah, that's
and
correct.
It's quite new, but I haven't gotten a chance to go into it yet. It's 2 or 3 years old now.
Yeah.
And I have a list of things I have to measure in there, so I'm just collecting all. So I will be there for 1 or 2 days in some time, probably.
Nice. I can also mention that we have done similar studies where we have taken into account the spectrum of the source.
Yeah.
And used kind of sources which are maybe a bit more flat, like hi-fi speakers instead of an omni source, and see then kind of both, not just the peaks and dips, but the kind of amplitude of everything matching very well. And this is on our website. If you go to resources and validation cases or something like that, then you can see examples of this.
And as I said, the curve is rather flat in the 30 to 50 Hertz range. There might be a 3 to 5 dB difference. So in that range, you could see that the amplitudes, they lined up quite closely. But then there are always some, since this is not, I mean, I would like to emphasize this was not a scientific check. In the measurement, for example, I had the receiver on a tripod, and I couldn't get the tripod closer to the corner than 10 centimeters, for example. So it is good enough for the lowest modes, but as you go higher up, the more errors you will get. You will get constructive and deconstructive boundary interference. And then the source in treble also can't be closer to a surface than 40 or 50 centimeters. Whereas in real life I had it up to the corner, so you're not getting as much excitement the higher up you go in frequency within treble with that setup. Yeah. So this was, as I say, a more of a rough check that I made just to convince myself that, you know, the frequency response is at least in the same ballpark.
Right. Yet another thing we're working on, improving how close you can place the source to the wall. All right, there are several more questions here. Measurements can be imported and used as initial data for the simulation. I guess we kind of covered this one. Question that was from Roy, so thanks for a good question. From Theo, have you compared an actual recording with a simulated one? Well, we have certainly seen here today examples of, you know, frequency responses, reverberation times being compared to simulations and measurements and seeing some good results. And on our website there are several other kind of comparable validation cases. And then indeed we've also compared oralizations, at least here on Treble's site, and where we hear very convincing results and very kind of comparable. It sounds quite comparable between the measurement and the simulation. So that's quite cool. Assuming that you have kind of rather controlled scenario where you know the material properties and things like that, then you can get convincing results.
I'm speaking for myself. In this room, the only thing I tried, because I'm used to speaking to my coworker, and I put a single source in there, like a talking source, and it was quite agreeable with what I would expect. I mean, the results were good in the case of this room. And as I say, I mean, the low frequency simulations, or just the wave solver in general, produced some very, very good results, so that was as I expected.
Right.
But I haven't done any major, I haven't tried to go in there with a saxophone.
Right. Okay. Let's see here. Okay, here's a question. Is it possible to export auralization results to, for example, WAV files using your web or SDK platform? It's definitely possible in the SDK. In the auralizer or in the web tool, you can download the WAV files of the impulse responses, and then you could convolve that yourself to create a kind of offline auralization, let's say. But now, of course, you also have the ability to create these kind of standalone auralizations, which you can share through the web and open kind of in any device without even logging into Treble or anything. So you have these kind of different options, I guess, for outputting audio output out of Treble. What are the limitations on room size? Maybe I can give a quick comment, and then you can also kind of share your experience.
Yeah.
In principle, you can simulate any size of a room in Treble, ranging from tiny to a stadium, but then it's a question of how high in frequency you want to go with the wave solver, and then it's sort of I guess kind of a balance between accuracy on the one hand and kind of computation time on the other. As the space, volume of the space increases, it becomes computationally heavier and heavier to go up with the wave solver, but then again also the kind of wave phenomena gets concentrated to lower and lower frequencies as the space volume increases. So that's sort of the general principles, but maybe you can kind of tell us your sort of...
Yeah, so the smallest room I've simulated in Treble was basically a glorified cupboard in a music school that they were starved of space, and they placed 2 pianos in a room that was 2 meters by 5 meters and then 3 meters high, so extremely tiny. And the thing about that was actually, if you have such a tiny room and then you place 2 pianos into the room, the pianos will have a major impact on the sound field. And I used Treble, actually, the way I used it was that I had done these checks on my own office, so I could trust Treble to accurately simulate the results, and then I kind of used it to deduce the effect of the pianos on the sound field, because you have 2 like resonating boxes, basically, that carry a lot of absorption. And I used that, basically, so I measured the room as it is, without any treatment, with the pianos, placed all the relevant parameters on all surfaces, and then basically put the parameters on the pianos that were missing to make it fit. And I did that because I could trust Treble that it would accurately simulate even this tiny room. And then from that I designed the acoustical treatment, and it turned out quite well. As good as you can get in a cupboard like this with 2 pianos at least. I'm currently working on a huge hall. I can't remember how big it is. It's like 1,000 square meters or something, and that has a height of 7 meters. But that's still a work in progress. So I haven't done. This is my first foray into modeling huge rooms in Treble. So I don't have much to say as of now, but soon.
Yeah. We've certainly had many customers who've simulated like stadium-sized venues with good results.
Yeah. And then using only the geometrical.
Yeah, or maybe, if you have a very large hall, then maybe you would simulate the lowest 2 octabands, maybe in 3rd octaband also 250 Hz wave-based, depending on how long you're willing to wait.
Yeah.
But then it's just kind of a few minutes, maybe up to an hour, the simulation. And then, for smaller rooms, maybe go up to 1-2K, and then it just still takes a couple of minutes.
Yeah.
Sort of something in that range. Okay, let's see here. More questions. Is it possible to integrate Treble onto my own website with the SDK, or is there a tool or plugin available for that through an API? So basically, the SDK is very well suited for this. It's a Python-based interface, so you can really kind of plug it into anything as long as you can program Python against it. That's one option, and then the other option is the auralizer, or this standalone thing. Soon we will allow people to or this is at least something we're exploring, that you could kind of embed these kind of standalone oralizations into your own web page and things like that. Thanks for the good question. Let's see. 2 or more sources simulated simultaneously. So you can simulate as many sources as you want in Treble. They're all run in parallel, so it doesn't increase the compute time or anything. But then, as we talked about earlier, viewing results where you have many sources at the same time is something that we are working on right now.
One question from me, can you get the average from all sources at the same time?
That's kind of part of that initiative. So Q1 24, if all goes well. Here's someone who says he or she is excited about the SDK and is on the waiting list and wondering when access will be granted. And as I mentioned in my presentation, we have been sort of rolling out the SDK in a let's say, controlled fashion to early adopters, and want to. This has been going very well. We've been getting great feedback from the initial users, and now, probably already in January, most, if not everyone, on the waiting list will be granted access, or trial access, to try it out. Okay. Here's one for you, Ólafur. You said design a Helmholtz resonator. How did you implement that into Treble?
Yeah, so the way I did that, it was actually a slit panel resonator. So basically a Helmholtz resonator, but over a whole wall with slits in the panel. And I used I designed it not in Treble, but just using the, well, at least the Danish method. I don't know if it's a German method originally. The one you are taught, at least we are both from DTU. So the one we are taught at school, and devised the resonance frequency of the absorber from there, and then just used my own experience to input the absorption coefficients into Treble that I thought were correct. So this was a very, as I say, and this is kind of one of the reasons I've been kind of, why I don't want to import too much, because then you also have to worry about the rigidity and the impedance and things like that. Mm-hmm. So this was just thinking about it from the point of view of the absorption coefficients that I had already designed, and then just created the material within Treble with those absorption coefficients. But as you say, if you implement soon a bit more powerful tool to create materials where you can just define the material within Treble itself, mm-hmm. and do these calculations, because these are just rather simple calculations, just some simple algorithms really. Mm-hmm. And if you can start doing that within Treble, then that would obviously be, and define the material, so Treble could then more approximately deduce the impedance and the relevant data. Yeah. So I think when you roll that feature out, I would be more comfortable with implementing Helmholtz resonators within Treble. That being said, when I did this, it was in a rather large music hall, and the results were actually really good. So I got it to fit with measurements in a really good way that I couldn't get with geometrical solvers, even though the hall was around, I think, 1,500 cubic meters. So it was not a small room, but the wave solver made a huge difference in that case. Mm-hmm. Mm-hmm. But the point is, it was just placement. I just inputted the absorption coefficients that I had already calculated.
Right, right. I think we are kind of running out of time, but I think let's go for 3 more minutes, since there are a couple of more good questions here. But you know, feel free to tune out if you had enough for today. So there's a question here about sources can sources be closer than 0.5 meters in Treble? Let me elaborate just briefly on why this is a limitation right now. So it has to do with the wave solver, because the way we model a source in the wave solver is that it kind of takes up some space. It's kind of a pressure distribution around the coordinate point of the source. Okay. And if you put it very close to a wall, then this pressure distribution kind of gets a bit messed up, so you don't get like a flat frequency response out of it. Mm-hmm. So it's really a limitation of, let's say a limitation of the wave solver, or the way wave modeling is done. Mm-hmm. In the geometrical part, there is actually no limitation. So what we will probably change to in the very short future is that you can put it as close as you want, but you will receive a warning. The wave results at the lowest frequencies might not be entirely correct because you placed the source very close to the wall. Mm-hmm. And then a bit longer term mission is to actually develop a source modeling strategy in the wave solver where you can place it as close to as you want. This is doable. We're not reinventing the wheel here, but yeah, it's a bit of a longer term mission. Are you planning to show source loudspeaker 3D artwork in the model? Yeah, that's a very interesting. I haven't actually thought so much about that, but that's a very good idea. Definitely something that would be cool. Danny asks, is there a difference in the processing power between the suite and the SDK? Right now, the suite, the web app, only allows one GPU at a time, whereas the SDK product actually allows you to run multi-GPU jobs. So you can both run kind of bigger jobs, meaning they can go higher in frequency with the wave solver, and you can run them faster. Maybe in the future we will also allow this in the simulation suite. Nate asks when the shared organization feature is going live. It's already been live for some of our beta testing partners, and already next week it'll be live for everyone. Yeah, similar question. When are the new features going live? More or less all of them are either live now or will be live next week. The only one that I showed today, which will be live in January, was the sharing of spaces. Okay, I think we have covered it all as far as I can see. Last question here. Will you be able to make source presets? As an example, making a band on a podium with multiple sources and saving that as a preset. Yeah, I think you can. I would argue that you can already do this in Treble. So you can certainly place sources anywhere you want. You can EQ them, the source power of them, the directivity, tune these things, and save it all in your setup and in your organization as well as a preset. If it's not clear, then please reach out to us in our live chat, for example, and we can show you how. I think that's it for today. It was a great session.
Yeah,
good discussion.
Thank you very much for having me.
Thank you for coming, Ólafur.
Very interesting and fun to be here.
Great to have you,
Thank
and thanks for the good collaboration so far.
Yeah, thank you too.
Okay, so we just say bye from Reykjavik.
All the best.
Thanks for tuning in.